This lecture is about the ordinal logistical regression for sentiment analysis. So this is our problem setup for a typical sentiment classification problem, or more specifically rating prediction. We have an opinionated text document D as input, and we want to generate as output a rating in the range of 1 through k. So it's a discrete rating, and thus this is a categorization problem. We have k categories here. Now we can use a regular text categorization technique to solve this problem, but such a solution would not consider the order and dependency of the categories. Intuitively, the features that can distinguish category 2 from 1, or rather rating 2 from 1, may be similar to those that can distinguish k from k minus 1. For example, positive words generally suggest a higher rating. Now, when we train categorization program by treating these categories as independent, we would not capture this. So what's the solution? Well, in general, we can add order to a classifier, and there are many different approaches. And here we're going to talk about one of them. It's called ordinal logistical regression. Now, let's first think about how we can use logistical regression for a binary sentiment categorization problem. So suppose we just want to distinguish positive from negative, and then it's just a two-category categorization problem. So the predictors are represented as x, and these are the features, and there are m features altogether. Each feature value is a real number, and this can be a representation of a text document, right? And the y has two values, binary response variable, 0 or 1. 1 means x is positive, 0 means x is negative. And then, of course, this is a standard two-category categorization problem. We can apply logistical regression. You may recall that in logistical regression, we assume the log odd of probability that y is equal to 1 is assumed to be a linear function of these features as shown here. So this would allow us to also write the probability of y equals 1 given x in this equation that you are seeing on the bottom. And so that's a logistic function, and you can see it relates this probability to probability that y equals 1 to the feature values. And of course, beta i's are parameters here. So this is just a direct application of logistical regression for binary categorization. What if we have multiple categories, multiple levels? Well, we can actually use such a binary logistical regression program to solve this multi-level rating prediction. And the idea is we can introduce multiple binary classifiers. And in each case, we ask the classifier to predict whether the rating is j or above, or the rating is lower than j. So when y sub j is equal to 1, it means rating is j or above. When it's 0, that means the rating is lower than j. So basically, if we want to predict a rating in the range of 1 through k, we first have one classifier to distinguish k versus others, and that's our classifier 1. And then we're going to have another classifier to distinguish k minus 1 from the rest. That's classifier 2. And in the end, we need a classifier to distinguish 2 and 1. So altogether, we'll have k minus 1 classifiers. Now, if we do that, of course, then we can also solve this problem. And the logistical regression program would be also very straightforward, as you have just seen on the previous slide. Only that here we have more parameters, because for each classifier, we need a different set of parameters. So now the logistical regression classifier is indexed by j, which corresponds to a rating level. And I have also used alpha sub j to replace beta 0. And this is to make the notation more consistent with what we can show in the ordinal logistical regression. So anyway, so here we now have basically k-1 regular logical regression classifiers. Each has its own set of parameters. So now with this approach, we can now do rating prediction as follows. After we have trained these k-1 logical regression classifiers separately, of course, then we can take a new instance and then invoke a classifier sequentially to make the decision. So first, let's look at the classifier that corresponds to level of rating k. So this classifier will tell us whether this object should have a rating of k or above. And if its probability according to this logical regression classifier is larger than 0.5, we're going to say yes, the rating is k. Now, what if it's not as large as 0.5? Well, that means the rating is below k, right? So now we need to invoke the next classifier, which tells us whether it's above k-1. It's at least k-1. And if the probability is larger than 0.5, then we'll say, well, then it's k-1. What if it says no? Well, that means the rating will be even below k-1. And so we're going to just keep invoking these classifiers until we hit the end, when we need to decide whether it's 2 or 1. So this would help us solve the problem, right? So we can have a classifier that would actually give us a prediction of a rating in the range of 1 through k. Now, unfortunately, such a strategy is not the optimal way of solving this problem, and specifically there are two problems with this approach. So these equations are the same as you have seen before. Now, the first problem is that there are just too many parameters. There are many parameters. Now, can you count how many parameters do we have exactly here? Now, this may be an interesting exercise to do, so you might want to just pause the video and try to figure out the solution. How many parameters do we have for each classifier? And how many classifiers do we have? Well, you can see the answer is that for each classifier we have n plus 1 parameters, and we have k-1 classifiers altogether. So the total number of parameters is k-1 multiplied by m plus 1. That's a lot of parameters. So when the classifier has a lot of parameters, we would in general need a lot of data to actually help us, training data, to help us decide the optimal parameters of such a complex model. So that's not ideal. Now the second problem is that these k-1 classifiers are not really independent. These problems are actually dependent. In general, words that are positive would make the rating higher, and for any of these classifiers, for all these classifiers. So we should be able to take advantage of this fact. Now, the idea of ordinal logical regression is precisely that. The key idea is just the improvement over the k-1 independent logical regression classifiers. And that idea is to tie these beta parameters. And that means we are going to assume the beta parameters. These are the parameters that indicate the influence of those weights. And we're going to assume these beta values are the same for all the k-1 parameters. And this just encodes our intuition that positive words in general would make a higher rating more likely. So this is an intuitively appealing assumption. It's reasonable for our problem setup when we have this order in these categories. Now, in fact, this would allow us to have two positive benefits. One is it's going to reduce the number of parameters significantly. And the other is to allow us to share the training data, because all these parameters are assumed to be equal. So these training data for different classifiers can then be shared to help us set the optimal value for beta. So we have more data to help us choose a good beta value. So what's the consequence? Well, the formula would look very similar to what you have seen before, only that now the beta parameter has just one index that corresponds to the feature. It no longer has the other index that corresponds to the level of rating. So that means we tied them together, and there's only one set of beta values for all the classifiers. However, each classifier still has a distinct alpha value, the alpha parameter. The intercept, it's different, and this is of course needed to predict the different levels of ratings. So alpha sub j is still different. It depends on j. Different j has a different alpha, but the rest of the parameters, the beta i's, are the same. So now you can also ask the question, how many parameters do we have now? Again, that's an interesting question to think about. So if you think about it for a moment, and you will see now we have far fewer parameters. Specifically, we have m plus k minus 1, because we have m beta values and plus k minus 1 alpha values. So that's just basically the main idea of ordinal logistical regression. So now let's see how we can use such a method to actually assign ratings. It turns out that with this idea of tying all the parameters, the beta values, we also end up having a simpler way to make decisions. And more specifically, now the criterion whether the predictor probability is above, is or at least 0.5 or above, and now is equivalent to whether the score of the object is larger than or equal to negative alpha sub j, as shown here. Now the scoring function now is just taking a linear combination of all the features weighted by beta values. Right? So this means now we can simply make a decision of rating by looking at the value of this scoring function and see which bracket it falls into. Now you can see the general decision rule is thus: when the score is in the particular range of alpha values, then we will assign the corresponding rating to that text object. So in this approach, we're going to score the object by using the features and the trained parameter values, beta values, and this score will then be compared with a set of trained alpha values to see which range the score is in, and then using the range we can then decide which rating the object should be getting, because these ranges of alpha values correspond to the different levels of ratings, and that's from the way we train these alpha values. Each is tied to some level of rating.